And it is a pleasure to have Francesca Tombari today, and she will tell us about what's behind the homotopical decomposition of a simplicial complex.
That's right. All right. Thank you for the introduction. And I've already thanked the organizer, but let me thank them once more for this great opportunity and this great idea of this workshop. So I've already, this talk that I'm going to give is based on work that I already presented in the Vietoris-Rips seminar series. However, if you were there, you won't be too bored, I hope, because now we are going to see a new perspective on I mean, not a new perspective, but what's the math behind the theorem about homotopical decompositions that we proved. In case you were not at that talk, that's not a problem at all. This is completely going to be self-contained, and that's it. So this is a work published last year, written jointly with Wojciech Chachólski, Alvin, Martina, Scolamiero, part of the TDA group at KTH. Let's get started then with a little bit of context. So we start with a simplicial complex K and take a decomposition of its vertices, and here K, oh no, this is not what I wanted. K0, which is a collection of vertices of the simplicial complex. We take a covering of them by two subsets X and Y. When we restrict then the complex to the set of vertices X and Y, we obtain two subcomplexes of K. And their union will still going to be a subcomplex of K, right? That we refer to data-driven decomposition of K. The reason is that this is not the usual decomposition that one does for simplicial complexes in algebraic topology, but it arises from applied topology. So when we take a simplicial complex arising from a metric space, we might consider, okay, let's subdivide our initial cloud of point and cover it by two subsets, and then take, for example, a Vietoris-Rips complex or a Czech complex out of it. Well, if we take the union of these two, then the homotopy type of this union is not going to be the same in general of the homotopy type of the Vietoris-Rips complex of the total space. And this is exactly the same problem, but stated in general for a generic simplicial complex. And an example of things that might go wrong when taking a decomposition instead of the total simplicial complex is this. So your K is, our initial K is this square here. And if we take the decomposition given by the two vertices on the left, and they give your X, two vertices on the right, and they give Y, restricting K to these sets, we get these two edges. Of course, this is not a homotopy equivalence because they are like completely geometrically different objects. So the data-driven decomposition has two connected components, whereas K has one cycle, and the data-driven decomposition has none. So they are very different, right? And so we wonder, can we measure the difference between these two objects? Or in other terms, can we provide circumstances for which actually K, the homotopy type of K, can be recovered from the homotopy type of this data-driven decomposition? Those are the kind of things that we think about. And now, what are the techniques? What are the tools that we use? What's our fil rouge, basically? I'm going to tell you this, but in general terms. So let's start with a functor from between two small categories, I and J. Let's say that we want to study the properties of this functor. And here I'm on purpose vague, but soon we are going to see some examples. But when I say properties, I mean homotopical properties. And here I am doing a jump in the sense that I am hiding the fact that actually I'm considering the nerves of the two small categories and functor induced on the nerves to study their homotopy type. Anyway, if we want to study such properties, we may go to the homotopy fibers of this functor, and which gives us some sufficient conditions, again, some features, some properties to state something about the functor. But we do one step more, because the homotopy fibers are built out of comma categories. And I'm very not precise here, but please keep these words as ideas. But so the comma categories are these categorical fibers, and that are the building blocks of the homotopy fibers in some sense. Here I decided to skip the definition of homotopy fibers but give you the definition of comma category. The reason is that our goal today is to understand the functor F, some properties of them, by looking at the categorical fibers, hiding the fact that actually we are studying the homotopy fibers in the middle. Anyway, a comma category, I'm just going to define this F over J, where J is a fixed object in the landing category, capital J, are categories that are formed by pairs. The first element, the first entry is an object in the indexing category I. The second entry is a morphism from the image under F of I to this fixed object J in the landing category. Morphisms here are then going to respect these pairs, so they are going to be a morphism between the first entries, so between objects in I, and commutative triangles that respect this second entry. Great. In what sense did I tell you before that these comma categories are the building blocks of the homotopy fibers of the functor? Well, if you fix a closed class, and here again, I'm avoiding the definition of closed class, but in words, this is a collection of connected simplicial sets that are non-empty and closed under weak equivalences, wedges, and homotopy pushouts. But we are going to see some examples in a second. So if you don't remember, don't worry. But what do we want to do with this closed class? Well, it happens that if these categorical fibers are in this closed class, then also the homotopy fibers of the functor are in the same closed class. This is a theorem, and you can find it, and here you have a reference. That is a work of Wojciech of a while ago. And here maybe I should make a honor statement, which is that he's the actual expert about these things. I'm more of a practitioner, learn these things to be applied in the context of our decompositions and in particular on Vietoris-Rips complexes. That's another story. All right, examples I promised. If an example of closed class is contractible simplicial sets. So if you have your comma categories all contractible for a functor f, then that functor turned out to be a weak equivalence, and this is going to be or homotopy equivalence in our context later.
For all j?
Sorry?
For all j's, you mean?
For all j, yeah.
Okay.
Absolutely, that's important. Yeah, I avoided writing too many words with the risk of being imprecise, but yes.
Thank you.
And or another example, if all your comma categories are unconnected, then it turns out that F induces an isomorphism on whole homotopy groups up to degree n, and a surjection in degree n+1. This, we are going to see an example of this. Or even more, if you have connected fibers and with p torsion up to degree n, then F also induces an isomorphism up to degree n in homology, but with coefficients in ZQ with Q, another prime different from P. And again, a surjection in n+1 degree. Or even more, if the comma categories are acyclic with respect to some homology theory, then F induces isomorphism in the same homology theory. So those are all the kind of, all examples of closed classes that in which the categorical fibers might belong and tell you something about the functor. But this was all very general. Remember that actually we want to study this map, not a generic functor between small categories. This is just an inclusion map of simplicial complexes. They can indeed be seen as categories, as poset categories, with objects being their simplices and morphisms being their inclusions of simplices. So the comma categories also turn out to be not that complicated. They are, if you fix a simplex sigma in K, then the comma category iota over sigma is going to be formed by these simplices tau and an inclusion of tau into this sigma. All right. With that in mind, let me introduce our leading character, which is called obstruction complex. This is a simplicial complex associated to a decomposition of the simplicial complex K. Here, as before, I take such a data-driven decomposition, and from now on, A here is going to denote the intersection of the two subsets X and Y covering the vertices of K. So now fix a simplex in K, then its obstruction complex is the collection of subsets of A that are non-empty and that together with sigma form a simplex in K. This is nothing else but the intersection of the star of the simplex together with K restricted to the intersection A. This is just much easier with an example. The entire picture is your simplicial complex K. Now we are interested in finding the obstruction complex of sigma, which is just this edge V0, V1. So of course, not of course, but according to the definition, A0 is inside the obstruction complex because together with sigma, it forms a triangle in the complex in K. Same for A1. However, the edge A0, A1 is not in the obstruction complex because there is no tetrahedron formed by these four vertices. So the obstruction complexes are subcomplexes of K, and they might have all the possible different homotopy types and being empty as well. That's a possibility too.
Francesca?
Yes.
So in this picture, X is a set of V0 and V1, and Y is a set of A0, A1, and A2. Am I correct?
Yes, you're correct. I didn't specify it, but yeah. So this A0, the important thing is that A0, A1, A2 are the intersection. Yeah, exactly. I didn't specify X and Y, but yes, absolutely.
Thank you.
Thanks for pointing it out, actually. All right. One more ingredient to this story is this collection P of simplices of K. This collection is formed by all these simplices that have vertices both or either entirely contained in X, so imagine this to be X, or entirely contained in Y, this is Y, or intersecting their intersection. So rho is one example of an edge being entirely contained in Y. Sigma instead is an example of a simplex, two simplex having vertices both in X and Y and also in the intersection. Equally important is actually its complement, K minus P, which then will be formed by simplices in K that both intersect X, like this, intersect Y, like these two edges, but do not intersect their intersection here. Okay. Right. What do we use them for? Well, first of all, we observe that they are subcategories of K, both of them. However, they are not subcomplexes. But we don't actually care because we just treat this simplicial complex K and its data-driven decomposition as posset categories, as we said before. So we actually forget that they are simplicial complexes for now. And so after observing that P is a subcomplex of K, we actually also observe that it contains the data-driven decomposition of K. So we can split the inclusion map of the data-driven decomposition into K with these two other inclusion maps, F and G. So we reduce, or better, we translate the problem of understanding the inclusion map before into understanding these two inclusion maps. The reason for doing so is that the first one, so F, turns actually to be always a weak equivalence. And this is proven by looking at its categorical fibers that we've seen before. And its categorical fibers turn out to be all contractible. So leading to a weak equivalence here. What does it mean? In other words, it means that if there is a difference in the homotopy type between K and its data-driven decomposition, it is not encoded into F because F preserves the homotopy type of the data-driven decomposition F and P. So the whole difference must be encoded in G, the other inclusion map. In what way? So we observed that for any sorry, there is a question. Is F always a homotopy equivalence? Yes. So I say weak equivalence, but actually I'm intending homotopy equivalence here. Yeah. Yes, P depends on the choice of X and Y, confirmed. So it's, but because the data-driven decomposition itself depends on the choice of the covering. So it's all decomposition dependent, what I'm going to say, even the obstruction complex, everything. Thanks for the questions. Those are very important points. So I was at G, right? G is, we observed that the comma categories associated to simplices in K, but also in P, are contractible. And in fact, they are weakly equivalent to the star of the simplex sigma. So again, they are not going to serve as obstructions for the homotopy type of the decomposition being the same as the homotopy type of K. what serves as obstructions are exactly the obstruction complexes. So if you study the categorical fibers associated to simplices in K minus P this time, they turned out to be weakly equivalent to the obstruction complexes of sigmas. So that's where the difference is hidden. That's what we want to understand to And this leads to our main theorem, which is a consequence of this fact that we just saw, which reads as follows. So fix a closed class, and now remember your first your favorite closed class from before, like contractible simplicial sets, for example, and assume that every sigma, every simplex in K minus P has an obstruction complex satisfying that closed class, or in that closed class, if you prefer. Then the homotopy fibers of the inclusion of the data-driven decomposition of K into K also satisfy the same closed class. And here, let me underline that, again, it's all about studying these simplices in this very part of the simplicial complex, K minus P. Okay, I forgot to put it there in advance in order to let you remember what was K minus P. Okay, and this now specifies in several ways, in several corollaries, according to the closed class that we choose. I apologize for the amount of words on this slide, and but please bear with me and let's go through it through at least 2 items of this list. So now let's say that all your obstruction complexes associated to K minus P are contractible. Then the inclusion map of the data-driven decomposition of K into K is a weak equivalence. So this, or homotopic equivalence, this is telling us, okay, you can, this is a good decomposition in order to understand the simplicial complex K by just looking at the data-driven decomposition. Or let's say that the obstruction complexes are n-connected, then also are the homotopy fibers, and then the inclusion map induces an isomorphism on homotopy groups up to degree n and a surjection in degree n+1. So maybe they are not homotopic equivalents, but still we can say something about their homology groups. And right, let's now particularize a little bit these theorems by adding an hypothesis to our initial simplicial complex. And let's take a clique complex as initial object, initial simplicial complex. For the ones of you who are not familiar with clique complexes, let me just state in a couple of words what they are. They are just simplicial complexes that are completely determined by their one skeleton. So namely, no empty simplices are allowed. So there are not going to be empty triangles, no empty tetrahedra, etc. So we can say something more specific in the context of clique complexes. For example, the following theorem. Let's start with K clique and take and assume that one of these two conditions are satisfied. First condition saying that there is L, an n-connected simplicial complex, for which L is equal to every obstruction complex of every edge of K minus P. The other condition says that there is that K restricted to A is unconnected, and for every edge in K minus P and every vertex in A, tau, which is this edge, union V is a triangle inside K. If one of these two is satisfied, then the homotopy fibers of the inclusion map are n-connected, same n as the obstruction complex is. Let's see it with a picture. So this is meant to be a click complex. So I just draw the one skeleton. However, you should think of it as all filled in. In fact, this is a triangulation of the cross polytope of in 3 dimensions. So there are 4 tetrahedra all glued properly. I just noticed that actually I messed up with the perspective, so it's okay. Anyway, I hope that the idea is clear. So in particular, let's observe, let's take this decomposition given by X is given by these 4 points in the middle, 4 vertices in the middle, plus this extremal left point. Symmetrically, Y is given by this 4 again, and this extremal left point. So, right point. So there is just one edge, tau, which I've highlighted here, which is in K minus P. Okay. So this is another picture of the same decomposition, in which instead I've highlighted the intersection in red, the intersection of the two covering of the vertices. Observe that this is actually also the obstruction complex of the previous edge that we considered tau. And this L is one connected. So this satisfies the first condition of the theorem, saying that there is one connected, in this case, simplicial complex, for which every obstruction complex is equal to, associated to an edge in K minus P is equal to L. Since we have only one, we are done. So this this allows us to conclude that then the homotopy fibers of the inclusion are also one connected. And this is reflected by this example. Indeed, you may observe that the data-driven decomposition is obtained by regluing this together, these two pieces, which is the boundary of the cross polytope this time, which is homotopically equivalent to S2. Whereas K, the initial simplicial complex, was a triangulation of the filled-in cross polytope, and so it was contractible. And again, maybe this is too silly example, but you may observe that then H0 and H1 are indeed isomorphic for K and its data-driven decomposition. Indeed, they are both 0, reduced homology I'm talking about. And there is a surjection from the degree 2 homology of the data-driven decomposition and degree 2 homology of K. So 1-dimensional, 0-dimensional. So this was maybe a little bit too silly also because this example I told you satisfies 1, but it actually also satisfies 2. Indeed, we have that K restricted to A is one connected, and every edge in K minus P, which is just this tau, form a triangle with every vertex in A. So this actually is satisfies everything. All right, let's see another type of result that we proved, it's the following. Again, starting with the clique complex. This time, in this clique complex, fixed decomposition, there are two elements, AX and AY inside A, that satisfies three properties, all of them now. So for every edge, tau in K, which has one vertex in A and one vertex in K minus A, tau together with AX form a triangle inside K. And a symmetric property for AY, and moreover, for every edge tau, this time in K minus P, the set the set tau together with AX and AY form a tetrahedron inside K. Well, if those three hold, then the inclusion map is a homotopy equivalence. So we can retrieve the homotopy type of K just looking at its data-driven decomposition. This is actually, okay, and here we have also an example that I took from, redrawn from another paper that you see linked here. They proved this, this result, and for metric gluing of the Vietoris-Rips complex of a metric graph. And I basically took the example and took inspiration from that theorem. I reproved it in our context for a generic clique complex. And so I decided also to take the very nice example, because it clarifies this all these conditions very well. So here you have your K that is, again, is just a one skeleton. So all the simplices that you see here, that of which you see the one skeleton, are considered to be filled in. It is, let's say that we want to decompose it in this way. So we basically separate the two almost evident octagons that we have, and their intersection is highlighted in red here. So just these three vertices and two edges. There are these AX and AY that are in the theorem, and they satisfy all of the properties. For example, take this tau, which has one vertex in A, one vertex in Y minus A. Well, that together with AY form a triangle in the simplicial complex K. And moreover, if you consider tau to be this this edge in K minus P, that together with AX and AY form a tetrahedron inside the simplicial complex K. So since all of them are satisfied, then we can conclude, all of the properties are satisfied, we can conclude that the inclusion, that K has the same homotopy type of the two pieces that we separated at the beginning. And so this turns out to be the wedge of two circles, because the intersection is contractible, so it collides.
Francesca?
Yes.
How many pages do you have?
I'm done.
Okay.
I mean, 1 second.
No problem. Yeah.
I just want to. Okay, thanks.
Mm-hmm.
I just want to conclude with the two observations. Actually, one observation, which is that maybe if you're working in applied topology, when I mentioned clique complexes, you thought about Vietoris-Rips complex. And they are indeed clique complexes, and we have worked towards this direction as well, and namely we translated conditions on the obstruction complexes of a decomposition of a Vietoris-Rips complex into metric conditions. So we basically didn't just look at the product, which is the simplicial complex, but we put some conditions on the underlying metric space in order to obtain, for example, contractibility of the obstruction complexes and connectedness of the obstruction complexes. This I've talked about in the other talk that I gave in the Vietoris-Rips seminar series. So in case you are interested in that, you might want to check it. And or what else? We might want to use this decomposition technique to maybe be applied to some particular simplicial complex that we want to study, and maybe try to find nice decompositions in order to obtain obstruction complexes that we can understand in order to say something about the complex itself. And yes, if you are interested, just check out the paper, or yeah, if you have something in this direction, let me know. Yeah, I don't have any new updates after that paper, but I find this a very interesting topic, so I'm very curious. All right, thank you all for attending, and I'm looking forward to any questions.
Thank you, and I suggest unmute ourselves to thank Francesca for this wonderful talk.
Thank you.
Any questions? I have one. For the first item of this page, do you have any example of some metric conditions on a metric space guaranteeing good condition on those obstruction complexes?
Yes, there are several. They are now I can't even remember them by heart because they are not that intuitive, let's say. but there are several. There were some of them were the most intuitive, let's say, could be understood even by looking at angles, for example, between edges formed in the Vietoris-Rips complex. So, or yeah, just looking at angles in your metric space, and that was maybe the most intuitive one. Yeah.
Mm-hmm. So you are saying angles on a metric space. Does that mean that you imply actually Alexandrov space?
No. I mean them embedded in Rn.
Ah, okay, got it.
Yeah, sorry.
Maybe I would want to make a comment because it was an interesting question. So you see, if you can perform Vietoris-Rips constructions on just distance spaces. Vietoris-Rips doesn't require triangle inequality. So an interesting question is whether these conditions do play a role, whether triangle inequalities does play a role when we perform metric gluings or not. And that's one of the aspects of this paper is that we actually find conditions where we do require triangle inequality. And which are not true for, let's say, arbitrary clique complexes or arbitrary distances. So
yeah, so it's not just only about taking a decomposition, but also starting with the correct hypothesis. No, not correct, but changing a little bit the hypothesis at the beginning, change the conditions a lot, or the outcome as well.
Francesca, I have a question. So you have you have general machinery, and then you sort of can focus in on click complexes. And then if you want, you could focus in further on Vietoris-Rips complexes. Is it correct to say that maybe you don't have as many specific results for check complexes because they don't even fit in the click framework, although they would fit in your general framework?
Yeah, exactly. That, to be honest, we have never investigated, but it is probably, I mean, yeah, as you say, we went through this pipeline of generic, click, and Vietoris-Rips to particularize the theorems, basically. But if one just jumps from generic, the generic results to check complexes, that might be of interest. Absolutely, it can be done.
Francesca, I have a question,
Yes.
which I think is related to the second bullet on this slide. But your data-driven decomposition is covering by two sets.
Yes.
Have you considered a more general situation, or anything
Yes,
to be gained
prepared.
by? Yeah.
No, wait. Probably better if I exit. Okay, I can't. I don't know how to exit this. Sorry. Okay, just be patient. I have to go through the next to the final slide. Too many animations.
That's never
Okay.
a bad thing.
All right, I was prepared because this is something that we took into considerations after we finished. It was a little bit complicated in general because you have to consider all the possible obstruction complexes given by all the possible pairings of subsets covering, and yeah, it was complicated, let's say. So we didn't figure it out in general, but we figured out a specific case, which is this this decomposition, where you basically have your simplicial complex K, and each piece of the decomposition is given by the whole complex by removing just one vertex. So it can be maybe pictured in this way for 3 elements. This is K restricted to A. So for this example, we realized that if you have a simplex, a subset of n+1 distinct vertices, if it does not form a simplex, then the decomposition is just equal to your simplicial complex. So that's it. If it does form a simplex, then so namely, if we are in this situation, for example, then the nth suspension of the obstruction complex of this simplex fits into this cofibration sequence, meaning that there is a long exact sequence in homology, and we can relate the homologies of these 3 pieces. So this is the case where we can say something in general. I mean, with a generic number of subsets covering the vertices.
Sorry, I also like to make a comment here. So that's of course an interesting question. The reality is that if you allow more than 2 sets to phrase these obstruction complexes, to phrase the statement, it becomes very complex. It's it's part of, like, maybe you have a spectral sequence. you have to consider, pairs, triple intersections, etc. It becomes very, very complex and becomes, as far as we understand, not very easy to phrase, except this case that Francesca now presented. The way we use the decomposition into two is by induction. You have, let's say 3 sets. So you first concentrate on 2 sets, and then, you solve that problem, and you add to that problem that you solve already another set. Okay, so it's induction, which by the end of the day is the same thing as phrasing the problem, globally, if you have 3 objects, three things. So yeah, but we have not found an easy way of phrasing that thing, except that. And by the way, we do use in the paper the induction that we take. 2 first 2, then we add another one, etc.
Yeah, thanks. That makes sense.
One other question. So these results can be applied to simplicial complex with infinite vertices. Am I correct?
With finite.
With finite? Okay. The reason why I'm asking this is because one of my interests is computing homotopic type of a Vietoris complex of like a sphere and sphere or infinite space. So I was considering. Okay.
Yeah, that's very interesting. I think so. We, for example, as an example of how to use these techniques, of course, we were aware of the fact that it's known what's the Vietoris-Rips complex of the circle, but we used it to see what happens if you sample points in the circle, and we used it also to give to give an example. That's where actually we use, as Wojciech was mentioning, that we use the induction. Somehow the induction of in these techniques, but not for infinite, for any manifold. It's just finite for now.
Okay, so I feel I have to add a comment. Now, there's no assumption we make on K to be finite. Actually, there's none of the generic statement uses finiteness, and neither of these, closed classes. Approximations or for homotopy fibers. So no, I mean, finiteness doesn't play a role here. Okay, of course, sometimes, what we like to do very often, all the examples we were finite, we could check by hand, we could list these obstruction complexes for various, but there is no finiteness assumption for generic theorems. Sorry, Francesca.
No,
it's okay. It's okay. Yeah.
Okay. Any other question? Maybe one last one. Okay. If not, I will stop the recording.